Hello, period 6. We ran out of time today. Something which happens often, but today we ran out of time badly, and maybe had 5 or 6, 7 minutes left of things to say that I did get to in the other classes. So, and we also ran out of time in those classes. So in period 6 we ran out of time worse. Here is the exact state of the board when the period ended. And I just think we needed another minute or two to digest everything that just happened here. What happened? We started with this hyperbola with vertices each A away from the origin and with foci C away. We picked an arbitrary point P on the hyperbola. We applied the definition of hyperbola to say that for any point whatsoever on the hyperbola, and in this case I choose points P and points D, the differences in the distances to the foci has to be a constant. So I know that AP minus BP is AD minus DB, and of course because D is collinear with my foci, I can easily compute the distance that D is from the foci, and we get that this is 2A. So then, oh, that was erased, but we thus took this defining property, or we took this property of point P, that AP minus PB is 2A, and we ran with it. We did the geometry as shown here to find expressions here in purple for AP and PB, and we did a lot of algebra, most of which got erased, but then eventually landed us right here. And then, okay, this was starting to be kind of panic time because we were running out of time. But this, I will say, I think I did say this in class, is kind of like the real equation of the hyperbola. It has in it A's and C's, and that's what the problem started with, right? We started with little a being the distance that each of the vertices is from the center, and we started with little c as being the distance that the foci are from the center, and so we should expect our final answer to have little a's and little c's in it. And so in some ways you could get by your whole life just with this equation. But we have a search for sort of meaning, and this is kind of a repeat of what we said in class, but we have in the formula for the ellipse this sort of other number, b, in addition to the length of the major axis and the distance between the foci, we have this kind of b which represents the sort of stretch in the y direction. And so we'd like to recover some kind of understanding with respect to hyperbola of that same thing. And that is possible. And so what I do is this move, which is kind of obscure, which is I introduce into a sort of completed formula a new letter not existing anywhere in the sort of previous introduction of the problem, in the previous specification of the problem. The letter B doesn't appear. And yet, I think that if I just make it appear by forcing that c squared minus a squared to be b squared, then I will get a better formula. And I do get a better formula now. I'll put sort of 2 stars next to this formula. I get a better formula. It's better because it's simpler, and it looks more like the ellipse formula, but it now contains a letter for which I have no understanding. And so in a perfect world, there would have been, 10 minutes left in class or something, for us to investigate, what is the meaning of this b? If this is going to be our formula for the hyperbola, then what does b actually mean? And in order to find out what b means, we must go searching for b in our original problem. And what did we define b to be? Well, we defined b such that b squared is c squared minus a squared. And so therefore, a, b, and c have this kind of Pythagorean relationship. And if A, B, and C have a Pythagorean relationship, then I should look for a right triangle. Okay, so this is what we didn't, that was kind of transition. This is what we didn't get to in period 6, but we did do in all of the other classes. So I really feel you have a right to this education. So let's do it now. And I'm not going to stop the video for this because it just takes a minute, but it does take a full minute. I want to erase all of this stuff here and get the fresh picture kind of back again. And okay, I've done it. Right, so what did we have? We had the original hyperbola. There it is. There's my point D and my point C and everything. Okay, great. And now the question is, what is B? And because this is a geometry problem, or was a geometry problem when we started, we should probably find out what B is. We should answer that question geometrically. So what is B? Okay, little b I refer to. Well, we have to find it somehow on this picture. And we need to find it such that a squared plus b squared is c squared. Therefore, I should be looking for a right triangle whose legs are a and b and whose hypotenuse is c. In other words, find a right triangle somewhere, one of whose legs is a and whose hypotenuse is c. And so, okay, well, we can begin to do this because after all, this is little a, so that's kind of exciting. And then, what's little c? Well, little c is this length right here. That's a little bit awkward because I don't want C to be there sort of collinear with A, overlapping with it. I want C to be the hypotenuse of a right triangle. So I somehow need to do something with this segment of length C such that it becomes kind of like a hypotenuse. I don't want it here, I want it like here, or something like that. And so, inspired by that kind of thinking, what I'm now going to do is I'm going to draw a quarter circle. So kind of, set your compass here at, set your compass, one point of your compass to be at the origin, and open up your compass to be wide, C wide, and sort of swing it this way. And what we're going to do is we're going to, I don't know how good of a circle that is, I guess it's not the worst thing in the world. Then we're going to have this point up here, 0, C. So okay, this is just a quarter circle of radius little c that I've just drawn. Well, if we do that, now this right triangle is forming before my eyes. Because where is the right triangle whose hypotenuse is C? Well, I guess there are two of them, but the one I'm looking at is the one that comes from going right here and going up. So if I let that be a right angle, and I go up to this kind of point on this quarter circle that I've just drawn, then this is C, because I made this circle to have radius C, and sort of now kind of appearing before my eyes is this segment B. So what is B? I have just discovered it on my picture. B is the number such that a squared plus b squared equals c squared. So B must be, the length of the segment that you get from starting at a vertex and constructing a perpendicular up until you meet a circle whose radius is C. Okay, that's very obscure, strange, unsatisfying, and sort of unhelpful, but at first. But it does give some kind of indication of sort of like what B is on a fundamental level, and then as a follow-up, let's kind of discover what B is algebraically. Okay, so with 1 minute left in class, or maybe we were even a minute over class, I launched into this crazy little piece of algebra, which is to say, take this equation down here, the one with the smiley face and the double star next to it, and let's manipulate it and solve for y in some sense. And so, yeah, you just, add y squared over b squared to one side and subtract 1, and I think this is pretty clear. Then we got a common denominator. Then I multiplied both sides by b squared, and finally I took the square root. Okay, and so I was kind of shouting this at you, at the very, very end of class or something on the day before Christmas break. I'm sorry about that. But here we have this kind of equation, and hopefully you see that this is just several Algebra 1 steps away from that equation. Let's put, 3 stars next to this one or something like that. So why did I bother doing that? I bothered doing that because this reveals the true meaning of B in a sense that's more useful to me. What I get out of this representation is that I now notice that for very, very large x, that root x squared minus a squared is pretty much just x. And what I said in class is if x is like 1,000, then 1,000 squared is pretty much 1,000,000, and a squared is negligible compared to 1,000,000. So it's still pretty much 1,000,000, and when you take the square root of 1,000,000, you get 1,000 back again. So in other words, you should feel already that root x squared minus a squared is basically just x. And so as x goes to infinity, y is looking more and more like b over ax. Okay, now some people aren't so satisfied with this, so it's possible to write this out a little bit more clearly. So let me do that now, just really fast. This will be done in like 2 minutes, this video, I think. Let me just factor out an x squared from inside this radical. I did this in periods 3 and 4. So if you do that, you get x squared, 1 minus a squared over x squared. And then the square root of x squared is pretty much x. Or if you want to be more precise, it's kind of plus or minus. But you get 1 plus or minus b over ax times a root 1 minus a squared over x squared. And I think generally speaking, people feel more confident that here, just sort of obviously as x goes to infinity, the stuff inside that radical is going to 1, and the square root of something that's 1 is pretty much just 1. So what this proves is what I also said in class, which is that for very, very large x comma y values on this hyperbola, the hyperbola is behaving linearly. That basically the hyperbola is going to look kind of like a line. And what this proves in a kind of an algebraic way is that hyperbolas have asymptotes. And I can even now draw these asymptotes. This is what I thought was worth doing, having made this this discovery of little b, or having postulated that this little b was something I should care about, having discovered what this b is geometrically, and having also rediscovered what this b is algebraically, I'll now sort of connect those two. Because the line with slope b over a through the origin, and this line has already been partially drawn for us, it's just that one, so I just kind of continue it, is a line that my hyperbola gets closer and closer to. Okay, and so that's what we got. Okay, and now kind of finally or something, I guess so now finally, well maybe I'll just stop there. This is not the greatest, but that's exactly what I did in periods 3 and 4. So maybe that's good enough for period 6 also. This is the line y equals b over ax, and this is the line y equals negative b over ax, and that is kind of what b is. B is the factor by which the hyperbola has been stretched. And so the larger b is in this formula, the greater the slope of the asymptotes are, and that stretches out the entire hyperbola. Okay, goodbye.